Good afternoon, everyone. My name is Martin Bichler. I'm from the Technical University of Munich, and it's my pleasure to chair this session on the highlights beyond EC. As you heard from Sven this morning, so the idea of this session really is to expose the community to work that is being done in neighboring communities, may it be AI, theoretical computer science, operations research, or economics, and maybe implant some new ideas on you. So you've also seen probably that there was a submission process, so people could nominate or self-nominate papers, and that's what happened. It has been very successful this year, I have to say. We got almost 20 nominations, which is a lot, which turned this into a really, really hot problem, let me say, right? So, because all of these submissions were wonderful, so very, very high caliber publications in related fields, and it made it a really hard selection problem, right? So you want to maximize the innovativeness of a paper, the quality, and at the same time balance in a way the distribution across disciplines. I tend to think of these types of problems not as optimization problems, but as problems that are almost undecidable in a way, right? So fortunately, Sven and Elias, they helped me in the sense that there were a number of prestigious colleagues as judges in the committee to do the selection. It was Dirk Bergemann, Tom Sandholm, Tim Roughgarden, and Steve Tadelis. And I really want to thank all of them for putting all the effort and energy into the selection process. So our job was to narrow down the selection, or these 20 papers, to say 6, and then we forwarded the selection to Sven and Ilya, and they then, depending on how the program shaped up, picked 3 out of those. And I have to apologize to all those submissions that we couldn't pick, because almost all of them deserved really to be presented here, but I'm very, very happy about the 3 papers that are being presented in this session. So we have one paper on mean field games, another one a little later on blockchain and transaction fee mechanism design, and a third one on the welfare effects of Facebook and social media more generally. So without further ado, let's get started with the very first talk. It's a paper by Bar Light and Gabe Weintraub that appeared in operations research on mean field games, on uniqueness results, and some comparative statics. Take it away.
Thank you for selecting us. So I'm very excited to be here in person. I guess they will show the slides soon. Oh. It's working. Yeah, so this is a paper on mean field games, joint work with my advisor at Stanford, Gabriel, or my previous advisor. So let me start with a brief introduction. So many markets have a large number of agents that interact over time. So you can think about online marketplaces like Airbnb or Amazon. You can think about the retail industry, manufacturing, and so on. Now, typically, one can think on an agent, maybe a firm, as having an individual state that represents a payoff-relevant feature. So it can be production capacity, maybe the quality of the products, maybe reputation, or in ad auctions, maybe something like budgets. Now, agents take actions that influence payoffs and future states. You can think about investments in improving quality, maybe marketing campaigns, in ad auctions it can be bids. And per period payoffs may depend on a static competition game. So it can be a pricing game or an auction. And states change over time, right, due to uncertainties and investment of the players. And this is not our invention. This is a common framework in the economic literature that you see this type of setups or frameworks. So let's see our framework. So this is a framework maybe to have in mind, the stochastic game framework. So there are states. So let's think about capacity competition, just as an example. So the state of each firm can be the production capacity, and at each period, the firms make investment, right, to increase capacities. And S, here it's the states of the other players, the other capacities. Now, the payoffs will depend on a static competition game. Think about pi, the payoff function will depend on some a competition game, and the firms make investment, and it will lead to a new state in the future that will depend on some shock zeta. There are some uncertainties, and of course on the investment of the firm and the current state and the states of the other firms. And then we move, or the system move to a new state, right? All the firms have new states. So that's kind of the framework to have in mind. You can extend it in many ways with types for each player, and we do it in the paper, but that's the framework maybe to have in mind for this talk. So what is a standard solution concept for this type of games? So it's Markov perfect equilibrium. It's just a refinement of Nash equilibrium that all of us know, and it just restricts the strategies to be Markovian, meaning to depend on the current states. Now, in this solution concept, players track competitor states and optimize given other players' strategies. And the curse of dimensionality kicks in very fast. Even for a small number of players, it will be very hard to solve computationally for Markov perfect equilibrium. And as I said, there are a lot of applications with many players, so this really limits practical applicability, especially for empirical applications where you really want to estimate the model. Now, to overcome these difficulties, a different solution concept was proposed, which we now call mean field equilibrium. And this received extensive attention in the last decade or so as a solution concept to these stochastic games. Now, mean field equilibrium essentially take advantage of averaging effects for model with large number of players. And there are, as I said, a lot of recent applications in dynamic oligopoly models, ad auctions, matching markets, control theory, experimentation design, and many more. Now, previous literature showed or focused on approximation. So the question was, is it a good approximation to Markov perfect equilibrium? And there are positive results. So when the number of players grows large, it is a good approximation for Markov perfect equilibrium. What remained unknown is conditions for uniqueness. So this was unknown even for simple models. Now, why we care about uniqueness? So we typically use mean field equilibrium to study counterfactuals in complex strategic systems. So you can think on a policy change, maybe a market design change, and typically researchers look on one parameter, right? A parameter maybe that they see now, and look what happens if we change this parameter, right? What is a new equilibrium? And it turns out, and actually there are examples from the literature, that if there are multiple equilibrium, counterfactual analysis will depend on the choice of equilibrium. And of course, the choice will depend on your algorithm, and it's sometimes arbitrary. So uniqueness really sharpens this counterfactual analysis. Now, so our main contribution, as I said, is to really identify conditions that guarantee uniqueness. And the key condition that actually we need is that player strategies are decreasing in their competitor states or their competitors' actions. The good thing is that this key condition naturally arises in many applications from the literature. So you can think on oligopoly models that were studied in economics and operations, reputation models, and also macro models. This condition actually hold. We also derive analytical comparative statics result. Okay, so not by simulation, analytical results. And we generalize some previous existence results also in this paper. So this is a bit abstract. Let's see a few examples that kind of motivated this work. So one example, which is kind of standard, is this quality ladder model. So here I have logic demand models. There are, of course, other demand models. And think about each firm as a state variable. For simplicity, it's just a quality, X. And there is competition between firms. So there are firms, there are consumers, and the consumer utility is something like in this Logit model. It has some utility that will depend on the prices and the qualities. So we can really solve this game. So this is a game, the pricing game between firms, get a Nash equilibrium. So this is a static per period game that we can solve, and then compute the profit function of the firms. What the firms are doing in every period, they also play in this static pricing game and also make investments to improve quality in the future. So A will be the investment, and there is typical dynamics in these models. They look something like depending on the previous state, some depreciation, plus the investment, right? So you can think about this K function as an increasing function, that if a firm invests more, it will have a higher quality, plus, of course, some random shock that captures uncertainties. Another example that you can think about is a reputation model. So here, think about the state of a seller as a rating and number of reviews. And sellers invest in their products in order to improve the reviews over time. I think in Airbnb, maybe Austin invests in cleaning their apartments. In eBay, maybe something like packaging. And the payoff will depend, again, on a static competition game. Again, think about some logic demand model or maybe a different pricing game, and some cost. So you can think about this cost, okay, D times A in this case, so firms invest A, there is some cost D, as maybe something that the platform can change, right? So maybe Airbnb can help the sellers in cleaning, right, to help them with that. So that's a type of a second model that we have in mind. The dynamics here will be the following. So the next rating, the next period rating will be some average of the previous rating, right? So you have also some dynamics. So that's kind of examples that motivated even this paper. So now, suppose that S is fixed. S is the measure of states of all the players. So each player expected discounted, that's what each player is maximizing, the expected discounted payoffs. And we know from standard dynamic programming under standard assumptions that there is some Markovian optimal strategy. Now, it's important to note to all our results, at least these uniqueness results, what we essentially require is to have some Markovian strategy. It doesn't have to be a discounted payoffs. You can have behavioral biases, like hyperbolic discounting. Maybe you train offline, so you do some Q-learning, and then you have still a Markovian strategy that comes from this training algorithm or some machine learning algorithm. What we require is that agents play according to some Markovian strategy, essentially. So what is a mean field equilibrium? What is a mean field equilibrium? So a mean field equilibrium consists of two things: a Markov stationary strategy and a measure of a measure that the players what state they are, so that describes the players' states. And a mean field equilibrium requires two conditions. So first, the policy's actual G is actually optimal given the measure. So players are actually playing optimal. And this measure is an invariant distribution given the dynamics that is generated by the policy. So this is what we call sometimes a stationary mean field equilibrium. So to see it maybe more clearly, think about the following. So there is a player in state xi, as a measure of the other player states is S, and each player chooses the optimal strategy, they use G, and then they move to a new state, right? So there is dynamics that they will depend on, of course, their strategy, it will depend on some random shock, and then we get a new distribution. What is a mean field equilibrium? It means that this new distribution is the same as the old distribution. Okay, so we start with a distribution, we get a new one, and they are the same. This is a mean field equilibrium. Okay, so Of course, you can write it mathematically as this like operator, such that a fixed point of this operator is a mean field equilibrium. But what are the difficulties? This operator is not linear, is not a contraction. So you cannot use something standard at least, okay, from the literature, so it's not clear how to approach uniqueness. What helps is all kind of monotonicity conditions that we assume. So we assume these monotonicity conditions over Q, where Q is a dynamics evolution for a single agent under the optimal policy G and under a measure S, so a fixed measure S of the player's states. And informally, of course, in the paper we have all the formal details, we show that under certain monotonicity conditions over Q, there exists a unique mean field equilibrium. So it also exists, it's also unique. Second, under the same monotonicity conditions, we derive sharp comparative statics results regarding the mean field equilibrium. So for example, take the quality ladder model. We can show how the average quality in the industry changes with parameters. So for example, we prove that it's increasing with the discount factor and decreasing with the investment cost. Now, two remarks maybe about these results is first, these games are not supermodular. So you cannot use this, for people here that know, all this machinery, right, from supermodular games. These games are not supermodular. So comparative statics results are actually pretty rare for games that are not supermodular, but we use uniqueness actually in the proof. It's important for the comparative statics results. And second, these assumptions are not on primitives, right? Because Q, the dynamic evolution of a single agent, will depend on the optimal strategy, for example. So these are not on model primitives. So if you have a model, you need to check if these conditions hold or they don't hold. And that's kind of what we do in the second part of the paper. We check and we show that actually a lot of, or at least a class of models from the literature have this condition. They actually arise kind of naturally in some of these oligopoly models and some of these macro models. So several models that this condition hold is first this quality ladder models that I showed you before, right? Second is dynamic reputation model that I also showed. There are other models like dynamic capacity competition, dynamic advertising models where this condition hold. Third type of models that are less known, I guess, for the audience here, but these macro models. Some of them actually also have these features, and they also have unique mean field equilibrium. So we discussed this also in the paper. Now, the key feature of all these models is that player strategies are increasing in their own states. This actually happens in many models, right? Because it's very Markovian, some of these models, and decreasing in the competitor states. Okay? So it's increasing in their own states, decreasing in their competitor states. So that's kind of the key condition that you need, and all these models have it, and that's why they have a unique mean field equilibrium. And we also derive sharp comparative statics result for all these models, as I said, even though they are not supermodular, because you see the strategies are increasing in their own state, decreasing in the competitor states. So this is clearly not supermodular games. Okay. So to sum up, we provide condition that ensures the uniqueness of mean field equilibrium. We show that a general class of models satisfies these conditions, and all these models have a unique mean field equilibrium. We derive comparative statics results that can be used to perform counterfactual or sharp counterfactual predictions with a unique mean field equilibrium. And we believe that this can be applied to other models of interest. So for example, if you think about market design problems in platforms, which many of us are looking at, it's very natural, right, to look on a large-scale limit, at least in some of the markets, because they have many, many players in these markets. And a second thing that especially for this audience is, okay, so I didn't present anything about the computation, right? Can we compute this equilibrium? Can you design algorithms that converge to this equilibrium? And this is actually generally pretty open to the best of my knowledge. There are some stuff, but this is pretty open. We don't know much about computation, algorithms that at least converge, that we can show that they converge to this mean field equilibrium. Okay, so that's what I had. Thank you very much. Yes.
Thank you very much for a wonderful talk, very interesting. So we have time for 1 or 2 questions. Yep.
Just a basic question to check my understanding. So one of the reasons one might want to use a dynamic framework is to understand how an industry will evolve over time in response to a merger or a policy change. Am I right that your framework is not useful for that type of application because you require a stationary equilibrium?
So I think you still, yeah, that's a great question. I think it's somewhat debatable, but I think you can think about, when you think from a single agent player, you can still think that when you change the mean field equilibrium, they optimize for like infinity. So you kind of change what they are doing dynamically also. It is true that the solution concept is stationary. That's what helps you with, of course, computation. But from a single agent, right, when you change something, you kind of change the optimization. And if you think about it algorithmic, okay, so there is convergence to this new, maybe like the path is very important as an empirical researcher, right? What is going on when you change the equilibrium until convergence. So there is, you can think about it as dynamics. At least that's how we think about it.
All right. Well, maybe one quick question. We've been talking about it earlier. So you alluded to computation. This is a very computational crowd. So can you elaborate maybe a little bit on the types of algorithms that are being used? You, I think, alluded to fixed point algorithms. And
so I think the most typical thing is to use what we call like a fixed point iteration, right? You can write your fixed point operator and try to iterate. So if this converges, yeah, it will converge to mean field equilibrium. But you can find examples that it just doesn't converge. And again, it's not contraction, so this won't work always. And now there are questions about what you mean first order methods, and that's not clear, like if this converge or not. So I think that's pretty open.
Excellent. Thank you so much. Then let's give a round of applause to our first speaker. And